Hi there, I'm Hao, and this is just another video of me solving random code problem. So let's begin. Today we have the design, add, and search word data structure. So we need to design a data structure that supports adding new word and finding it. If a string match any previous added string. Okay. Um, so we have two methods here, add word and search. Um, So for add word, we just add the word to the data structure and we can be matched later on. And return for the search, return true if there's any string in the data structure that matches the word or false otherwise. So the word may contain the dot, where the dot can be matched for any letter. So for search word like this, I'm thinking of we can use a try to keep track of this to do this problem. So let's look at an example here, right? So a try, we have a root node, right? And we will look at the children, right? Let's say it is B, we have bad, right? We have bad here. So B, A, and D, and we add that. So D, A, D, and math M, A, D. Right, so this is their the children. So you can think of a try um of a nested hash map. We can either use hash map or arrays to implement the try, but the hash map is much more flexible. We don't need to do any arithmetic to find the index of the array, right? So we're gonna have like a try node, right? And they're gonna have the children, right, which is an empty hash. And then we need to know when we get to the end of the word, right? Because many words might have the same prefix. For example, we have bad, right? But we can also do bat, right? So how do we know we are at the end of the word, right? So let's say we have that here, right? But we can also do daddy, daddy, right? Which means like we have one word here and one word here, right? So we need a flag to keep track of it, right? A boolean to keep track of whether the letter is marked the end of the word, right? So which means we can have the symbol here, right? Which is just a boolean indicating that okay, we are at the end of the word. So you can think of a hash map of a nested. Uh, you can think of a try of a nested hash map, right? Let's say we want to look at the word bad here, right? So we're gonna have a key of B. So this level gonna have three children, right? So B, this is D, it is N, right? So in each level gonna be a hash map, right? Uh, so B only one child, which is A, right? A, right? And then the children gonna be another hash map, right? And they have two children here, so D, uh, right? And then T. Just to be clear, this is the next level, another level. Use a different color here, right? So how do we search for a word? We can search for a word as if we search for the word bad, right? And we just have to iterate through every single letter. And as we iterate, we can just like look in the hash map, right? Which is like the children. Right? We can do let's say we have a try, right? Try of B, right? Try of B will return an object, right? The ping object here, right? And when I look at what? Look at the string of B, right? And then of A, which is the green map here, right? And continue, we can do a string of D, right? Which will give us the blue hash map here, right? So at any point in time, if we got any file, right, which means the word doesn't exist, we return any file. So that is how we search for the word in general, right? For inserting, it's pretty much the same, right? If it is if the word, let's say we want to add the word daddy, right? This word, um, we just iterate through the children, right? We look for the letter D. If it exists, we move on, right? A, D, and then the A, letter A. It's not exist yet, so we just add like a new try node, right? A new uh try node. Sorry, D, not A, D, and then Y, right? Same thing, right? And then because we get to the end of the input word, we just mark this at the end of the word, right? So that is how we add and search for a word in a normal case, right? So what if we have a dot here? So if you look at the example right here, b dot dot will return true, right? Uh, oh, actually, let's look at this one, dot id. So let me erase some of this so we can uh, have more space. Okay, we don't need to look at this anymore. Delete this. Also delete this. Okay, so let me change color here. So uh, as you can see, we have three words at end with AD, right? The dot mean we can match any characters, right? Dot can be matched with any letter, right? We have A and D. So uh so this has to be a word, right? So as you can see, we have the mark, the boolean here, the flag here, indicating that it is the end of the word, right? This is also the end of the word, and this is also the end of the word, right? And so let's say we search for um, dot .id, right? So we start from the root. If we see the dot, what does it mean? It means that we just skip the current level. We skip the current level and go to the next level, right? And update the letter. But the thing is that we need to search for we need to run a depth first search for every single children at this level. So if we are at the root level, then and we see a dot, then we need to run the DFS for each of the children, right? Each of the children. And if any of them return true, right, which means we have a word following this pattern, right? So we return true. If all of them is false, then we just return false, right? Yep. So whenever we see a dot, we skip. We increment to the next letter, and we run the DFS on each of the children, right? Each subtree. So a try is just like a poly tree, right? So we can search everything in log of n, right? In the binary tree, log 2, right? Now we have log like 26. If we have like 26 characters, yeah, 26 lowercase English letters, right? So on and so forth. All right, so that is a general algorithm. So yeah, let's code this up. So what can we do here? We can, first of all, we need a try node class, right? Class of try node. We need a constructor, of course. We need the children, the hash map, and then the boolean like error equal to false by default, right? And then we have the constructor. We need to create a try here equal to a new try node. Okay. So how do we insert? We have to iterate to if letters, right? Lines, and then I plus plus, and we have a char, right, equal to the word I. Okay. And then we need to check to see whether the character exists in the try, right? If it doesn't exist, we create a new try node for that and keep and if it exists, we just keep moving on, right? Okay, so char exists equal to char in try dot current, right? So we need a pointer. We need a pointer to iterating to our char, right? So uh so like a link like a linked list, right? If we want to move on to the next node, we have the next pointer, right? Like in a binary tree. But for try, then we just have to the key, the left and the right pointer will just be the key, right? We just input the letter, which is the key, and the value will return the hash map of the next level. Right? So try equal to this try. So if the character doesn't exist, we need to create a new try node, right? So we can do try dot children, right? And char equal to new try node, right? Because the next level is in the try dot children, right? And it is the key. Okay. If it exists and we just keep moving on, right? How do we move on? We move on by updating our pointer, right? So again, the char is the letter, the key, right? This will return the hash map of the next level. Okay. So if we get to the end of the input word, what do? We just mark the end of word for the current try node, right? The current letter. So if I equal to word length -1, you want to try dot children, right? Char equal to dot end of word and word equal to true, right? And we can just create a header method for this. So last index, passing I. So const last index equal to index equal to word length -1, right? If it is last index, then we set then the word to true. Okay, so that is how we add a word. So how do we search? So we need to run. We should do it in using recursion, right? It's easier and cleaner. We need to do like nested while loop and stuff. So what do we check in? We can think about it later. Right? It is the general structure that we want to have. So we're gonna start at 0. Okay, we need the index, right? The index the index of the index of the current word, right? That's called as I, which is the index here. Or just index to be clear. Okay. So what else do we need? We need the index, and then we need the index, but we also need the current pointer, right? To the current pointer of the level, right? So we can start at this as try, which is our tree, right? Our try, and we can keep iterating down to search for the word, right? So this we can call this current or current, right? So what is our base case here? Um, so if we current dot char, right? Char. So you need char, right? What is char? Char is our word index, right? And we can have like char exists equal to char in current. We need to return uh in current dot children, right? Okay. And if the char doesn't exist, then we return false, right? Hello? Okay, yes, sorry. Okay. So actually we're not gonna return false, right? Because we are doing the recursion now. So we need to think about it in the opposite way. So we all keep searching to the letter, right? So if the character exists, what does it mean? Which means it is not a dot, right? Because we never gonna add a dot to our a try anyway, right? Uh uh the word search, yeah, I think it's just English, yeah, lowercase, the word in search containing a dot or lowercase English letter. Okay. But I don't think we actually add the dot to our try anytime. So if the try exists, we want to keep iterating, right? So we can do current dot children, right? At jar, which is the pointer to the next level, right? And we're going to increase our index by one, index plus one, right? So current dot children char. So the char is a key, right? And the value will be a hash map of the next level, right? And we increase the index by one to look at the next letter in the word, right? And if the word doesn't exist, what do? We just return false, right? Um, so when we return true, if we were able to get through all of the letters in the word, right? Which means the word is found, right? Uh, so if we were able to get to the end of the word, which means index is equal to the word at length, right? And we're gonna return. So if we were able to get to the end of the word, then we need to make sure that the letter we are at, the last letter we are at, right, is the end of the word, right? Which is we're gonna check for the flag here. So we're gonna check for current dot end of word, right? You can just return this. Okay, so that is our general structure of how we gonna do this, like without the dots, right? So one more time, we're gonna start at the top of the root of the try and the first letter in the input word, right? We look at the character at the index, right? Which is char, and then we can check if the char exists, right? If it doesn't, if it exists, then we just gonna continue on to the next level, right? We look at the next letter by incrementing the index, right? And we pass in the pointer to the next level, right? Which is current churn jar, return and hash map to the next level, right? And then if we get all the way to the end of the input word, right? Then what do? We're gonna check that if the letter we are currently at mark the end of the word, right? If it doesn't mark the end of the word, which means this word doesn't exist in our chart. Okay. So, and if the chart doesn't exist, what do? We return false, right? But before we even return false, there's a special case, remember? So if char is equal to the dot, right? If char is equal to the dot, then it is a special case. We want to skip the current letter and run the DFS on each of the children, right? And so we can get the children by object.value of current of children, right? So remember the key will be the letters, right? A, B, C, D, and the value will be the hash map to the next level, right? So we want to get the hash map of the next levels here for each of the children. And then we're gonna iterate to the children length, and the I plus plus, right? And then we want to run the DFS, right, on the children, on each of the children, so children of I. And then also remember that we want to skip the current letter. We don't want to compare it or anything. We just look at the next letter if it is a dot. So index plus one, right? So we move to the next one. So we just do this for every single children. Remember, right? If so we reach the dot, right? We skip the dot and we go to letter A, right? We check A and D. So this line is the level here. So we are here, like this, the dot, right? And we do the DFS for each children here, each subtree, right? And if any of them return true, then we're gonna return true, right? If all of them return false, we're gonna return false, right? If any of the children, if any of the children subtree, if any of the subtree can find like the substring here with the word and with A and D, right? We're gonna return true. Okay, so we just have to check for that, right? If it is true, then we're just gonna start circulating and return true, right? And if all of them return false, then we're just gonna return false at the end. And that's pretty much it. So give it a try, accept it, submit, and thank you for watching.